All right, everybody. Hope you're all doing well. This is week 4, video number 2. This is our second video on your chapter 5 in your book. It's all about nuclear chemistry and nuclear reactions. So today we're going to talk about the last 3 things in chapter 5. The last 3 things that I think are important enough for us to know in chapter 5. And that is carbon-14 dating, nuclear fission, and nuclear fusion. All right? So let's just get started. At the top of page 1 of our notes here, we're going to start to talk about carbon-14 dating. So this is titled Detection of Radioactivity. Radioactive decay processes, in other words, radioactive decay reactions, generate high energy particles such as alpha particles, right? That was the helium nucleus. Beta particles, those were electrons. And then something called gamma rays, which are like high radiation, kind of like sun particles, if you will. These particles can produce ions when traveling through matter. And those ions, specifically an argon plus ion, which we'll write down in a bit, those ions can be detected. So a Geiger counter takes advantage of this. Now there's a picture of a Geiger counter in your textbook. I don't need you to know exactly what a Geiger counter looks like. All I need you to know is that Geiger counter is what's used to detect radioactivity. All right, so a Geiger counter will basically recognize argon ions and report back the amount of radioactivity in a substance. All right, so and I've written that down here. It says Geiger counter, picture in your book, measures radioactivity by capturing particles through a little window opening in the counter. Once inside, these radioactive particles ionize a gaseous argon atom to a gaseous argon ion. All right? And it's that argon ion, the argon cation, that gets detected and gets measured. All right? So a Geiger counter is what's used to detect radioactivity. Good enough. All right, now that we have that done, let's move on to the first of our 3 major topics for today. We got carbon-14 dating, then nuclear fission, then nuclear fusion. Chapter 5 is done. All right, carbon-14 dating. It's a method used for dating ancient artifacts made from cloth or wood. So carbon-based artifacts. Could be from cloth, wood, linen, like a shroud, something like that, or a wooden bowl. So carbon-14 dating originated in the 1940s by a guy named William Libby. He ended up winning the Nobel Prize for his work. All right, top of page 2 of our notes here. Still talking about carbon-14 dating, of course. Radioactive carbon dating is based on, as you might expect, carbon-14. Now, what I've written there in the box, if you remember, that's nuclear symbol notation. Excuse me, nuclear symbol notation for carbon-14, right? You got the A, then you got the Z. Z is the atomic number 6 for carbon. But carbon-14 is unstable, all right? So carbon-14 will decay into nitrogen-14 plus a beta particle, right? A beta particle is that electron I have right there. So carbon-14 is continually produced in our atmosphere. It's important to know that, because if carbon-14 is unstable, you would expect it to go away. But carbon-14 is also continually produced in our atmosphere, all right? So we have this kind of decay and this production. So this second equation is the production of carbon-14 in our atmosphere, where we have nitrogen-14 reacts with a high energy neutron. That little 10N is a neutron. So those two will kind of fuse together to make carbon-14 on a continual basis. So it makes an unstable carbon-14, which then again decays later on. And we also have a side product there of a hydrogen atom. So collectively, those 2 equations you have up there, the radioactive decay of carbon-14 followed by the production of carbon-14 in our atmosphere, it says, and it's got 2 stars there. So the concentration or amount of carbon-14 in the atmosphere remains constant over time because the above two processes, right, those two above reactions at the top of the page, occur at the same rate. So we're getting rid of carbon-14 in equation 1, but we're making carbon-14 in equation 2, and we're doing it at the same rate. So carbon-14 is constant in our atmosphere. In other words, so this is the last bullet point of page 2 here. In other words, on Earth and in our atmosphere, the carbon-14 to carbon-12 ratio remains constant. And by the way, carbon-12 is the main isotope of carbon. It's very stable. So that's always around. All right, carbon-14 dating. I'm now at the top of page 3 of today's notes, which you should be rewriting, right? Carbon-14 dating is used for wood or cloth artifacts. Why is that? Well, carbon-14 dating is used for wood or cloth artifacts because they're carbon-based, because they can come from plants, okay? Now, I got a double underline there on plants. I also mean trees or any type of wood-based material. As long as it's alive, it's carbon-14 to carbon-12 ratio. That's what the 14C/12C means. The carbon-14 to carbon-12 ratio is the same as the atmosphere's carbon-14 to carbon-12 ratio. So as long as you're alive, you're going to have the same ratio of carbon-14 to carbon-12. So if the tree or the plant is alive, then that's what we have, all right? But, so it's the second bullet point, but when the plant is cut down, or when the plant dies, the ratio of carbon-14 to carbon-12 begins to decrease because of the radioactive decay of carbon-14, all right? So when a plant is cut down, like to make a bowl, or when a tree is cut down, like to make an ancient log cabin or something like that, that's when that wood dies. So the time it takes to cut down a tree and make a cabin is only a few months or so. So in the long time frame, in the grand scheme of things, whenever you cut down the plant or cut down the tree, that's basically the age of the wooden bowl or the cloth, linen, garment, etc. that you might find in archaeology. Now, regarding that second bullet point there, but when the plant is cut down or dies, the carbon-14 to carbon-12 ratio begins to decrease. I do want to mention that carbon-12 on the left here remains stable, so its concentration remains unchanged at all times. All right, let's do an example. Example. Because carbon-14 has a half-life of 5,730 years, a wooden bowl having a carbon-14 to carbon-12 ratio that's half of today's current plants would be about 5,730 years old. Because remember, the 5,730 years, that is the half-life. That is the time it takes for half of the amount of the radioactive material, carbon-14, to go away. All right. There are two major drawbacks to carbon-14 dating, which I think are really important for you to know. Two drawbacks to carbon-14 dating. First, we're making a very big assumption. First of all, carbon-12 is always constant in the atmosphere. No problems there. But with number 1 here, we're making the assumption that the current atmosphere has the same carbon-14 amount as it did back in ancient times. So here we're assuming that the current atmosphere has the same carbon-14 to carbon-12 ratio as it did in ancient times, thousands, hundreds of thousands, even millions of years ago if you find something old enough. Number 2, you have to actually destroy some of the artifact in order to figure out how old it is. So number 2, a large piece of the artifact, roughly half a gram to 2 grams of whatever the artifact is, a wooden bowl or a wooden spoon or an old piece of wood that was used to make a cabin, etc. A large piece of the artifact must be destroyed because it has to get burned to form CO2, which is then analyzed for its radioactivity. So both 1 and 2 are drawbacks to carbon-14 dating. All right, so that's it for carbon-14 dating. Now we're going to talk about the last 2 topics. We'll kind of talk about them a little bit together, but we are going to separate them with a number 1 and a number 2. So nuclear fission Fission is splitting. And then nuclear fusion. Fusion is fusing or coming together. So nuclear fission, it's the splitting of a heavy nucleus into two smaller nuclei. Usually they're about the same mass. So it's kind of an even splitting, but not quite even. You don't get the same two nuclei. Nuclear fission, splitting a heavy nucleus into two nuclei with smaller mass numbers A. Nuclear fusion, on the other hand, is when you combine two light nuclei, in other words, two nuclei that don't weigh all that much, to form a heavier, more stable nucleus that does weigh a bit more. We're going to take a look at nuclear fission, number 1, and then when you see me write down number 2, you know I'm right. I'm going to start talking about nuclear fusion. So, some background: nuclear fission, late 1930s, Manhattan Project. Most of us learned about this in history class. This is the building of the atomic bomb, and this was done during World War II era. So it started getting developed in the late 1930s. They were working with a radioactive isotope of uranium, and that particular isotope was uranium-235. All right. So on the last page, I drew uranium-235. That's hyphen notation for the isotope. Here you see me writing it as the nuclear symbol notation, 235-92U. So uranium-235 nuclides, after being bombarded with neutrons, right? Neutron is a little 1, 0, N, and I'm going to draw it here in a second. Uranium-235 nuclides, in other words, nucleuses, if you have a hard time understanding nuclides, nucleus is. So uranium-235 nuclei, or nuclides, after being bombarded with neutrons, were observed to split into two lighter elements. Definition of fission, right? So here I have a neutron, far left, coming into contact with the uranium, and what does it do? It makes uranium-236, which is really unstable. So I put these little quotes around the uranium-236, letting you know it's not happy. It wants to split. And it does. It splits into krypton-92 and barium-141, two lighter nuclides, not similar, but close enough in size. Now, what happened there? Well, one neutron collided with uranium-235 on the far left, and the result was, now I've produced 3 neutrons as side products. What can those neutrons do? Start a chain reaction by reacting with even more uranium, right? So overall, you have uranium-235 plus 1 neutron yields barium-141 plus krypton-92 plus 3 neutrons. You can see how this is going to go downhill and make a chain reaction, and we'll write that on the next page. The nuclear fission process above releases 26 million more times energy than just burning methane. Burning methane is like a Bunsen burner. So you can see the advantages of creating a bomb that releases that much energy, right? Now, I said that 1 neutron collides with uranium-235, and I'm redrawing it here. And as a side product of the 2 lighter nuclides, the 2 lighter nuclides being barium-141 and krypton-92, I'm making 3 more neutrons. Well, that means I can now react with 3 more uranium-235s, make even more energy. This becomes a self-sustaining chain reaction. So what do I mean? Let's put that down in our notes. So the little arrow there says, the production of more neutrons in the above reaction makes it possible to have something called a self-sustaining chain reaction. Now let me give you a visual of what I mean by that. All right, so that circle right there is a nucleus. A nucleus of what? Well, uranium-235, right? And then I got my little dark circle, that's the neutron. And the little arrow just tells you that the neutron is making contact with that nucleus. In doing so, I have made 2 lighter nuclides, all right? Well, here's what I mean, okay? In the above reaction, I got 1 neutron going in. I'm talking above reaction, top of this page. I have 1 neutron going in, 3 coming out. So collectively, overall, one of these reactions makes net 2 neutrons, because it does take 1, but the output is 3. So that's where you get the 2 neutrons from fission in the really small writing there. So one fission reaction with the nucleus produces 2 net neutrons that can react with more uranium. All these little white circles are uranium-235s. Okay, so you got a neutron hits the nucleus of uranium-235. Well, now 2 of them can react with 2 uraniums. Well, the output on that is net gain of 2. So we go from, if you look vertically, you got 1 uranium-235. Now you can make a reaction with 2 uraniums, now 4 uraniums, now 8 uraniums, and so on and so on. This is a self-sustaining chain reaction. All right, so that's it for nuclear fission. Nuclear fusion, this is number 2. Besides nuclear fission reactions, an enormous amount of energy is also produced by the fusion of 2 light nuclei. These are generally done naturally in the sun and in stars where temperatures are extraordinarily high. That's one of the drawbacks of fusion, is that you require such ridiculously high temperatures that's really not all that achievable on Earth unless we have some really stringent guidelines. Example, stars, including our sun, produce energy via nuclear fusion reactions. So these are going to be 2 guys coming together to make something larger, right? Fusion reaction. So in our sun, which is 73% hydrogen, 26% helium, and 1% other elements. Well, in the sun, it emits a huge amount of energy, as you all know. It emits a huge amount of energy from fusion of protons to form helium. All right? So a proton is basically a hydrogen atom, but you take away the electron from the orbit. So a hydrogen atom is just 1 proton nucleus and a 1 electron orbit. If you take the electron away, you end up with a proton, which is an H+. So I've written it as H with a Z of 1 because the atomic number for hydrogen is 1, and then the mass number is 1 because you've only got 1 proton. So 11H. So 11H plus another 11H. In other words, 2 protons are going to make hydrogen 2. All right. Plus we get this weird thing called a positron, which is basically an electron with a positive charge. Don't worry too much about that. Now, that hydrogen 2, which we learned in earlier notes is called deuterium, or heavy hydrogen, deuterium. That can react with a 3rd proton, a 3rd 11H in the second equation. And that makes something called light helium, or helium-3, helium-3. All right, now 2 helium-3s can react and make a helium-4, which is an alpha particle. Okay, so the net result here is we have 2 protons, or 2 hydrogen 1s, making 2 alpha particles, 2 helium-4s. Now, one major problem with fusion, as I had already mentioned, is that you need extraordinary temperatures, unfathomable temperatures, not like turning on the furnace to 4,000 degrees or something like that. All right, so here on our next page of notes, we're going to elaborate a little bit more on nuclear fusion. And one of the problems with nuclear fusion is that protons, right, the 11H, which by the way means hydrogen's got a Z of 1 and an A of 1, right? So that means it's got 1 proton and then no neutrons. These protons repel each other. Basically, a proton's a +1. Another proton is also a +1. +1s are not going to want to attract to each other the way a ± would, like a magnet. So getting protons to fuse is very difficult because they both have positive charges. Now that's an electrostatic argument there. ± attract, + will repel, - would repel. These are ++. So protons repel each other electrostatically, so it's very difficult to get them to fuse, of course. To make these fusion reactions occur, to force 2 plus things together, scientists have to shoot protons at each other at very high speeds to overcome the huge proton-proton repulsion. Now we're talking speeds that, in order to get to these speeds, you require temperatures of 4 times 10 to the 7th Kelvin. Write down a 4 and then write down 7 zeros after it. This isn't something an oven or any industrial heater can get to, right? You require stars and the sun or conditions similar to it to make it happen. This is this is why nuclear fission and nuclear fusion just can't be done at home. All right. Anyway, that's it for chapter 5. So the two video lectures for week 4 video 1, week 4 video 2. Those are done. We now have all the lecture material that we need to get ourselves ready for exam number 1. So the best way to prepare is to go over all of the homework problems that you've been assigned from chapter 1 through chapter 4. Know how to do them. Know them so well that you just recognize the questions almost. Also, if you go back through all the video lectures, don't forget to pay attention to the notes. I mean, I've asked you to rewrite the notes, so I expect you to know the notes, and I'm going to ask you questions about our lecture notes. Also, there's a lot of sample problems I've done in the lecture notes that I might pull out from and change up just a little bit. Okay. I'm also thinking of making a chapter 5 solved homework problems video like I've done for chapters 1 through 4. So anyway, stay tuned and good luck getting ready for chapter 5 and your exam.